A linear polynomial is any expression that can be equivalently rearranged and represented in this, what we call expanded form. And the first time we talked about linear polynomials, I used the symbols mx plus b. I just use those letters because 100 years ago when I was in my 9th grade algebra class, they called it mx plus b. So m was the slope, b was the y-intercept. But I could equivalently just call these constants c1 and c0 with little subscripts. And that just tells you that, hey, these little c's are just numbers, right? They're just little constants. And I might call it c1 because this is basically the coefficient that multiplies x to the 1 power. And c0 is just that coefficient in my polynomial that multiplies x to the 0 power. But this is why I'm writing it this way. So x is a variable, c1 is the leading coefficient, c0 is the constant term. That's also the y-intercept if you graph this line. And every linear polynomial can also be represented in this factored form, where this time I'm saying a is the leading coefficient. And in factored form, you get to see what the root is. So the factor looks like, for instance, x minus r for whatever that root is. After talking about linear polynomials, we talked about quadratic polynomials next. And a quadratic polynomial is any expression that could be equivalently represented in this expanded form that looks like ax squared plus bx plus c. And again, those are the letters that we used in class for quadratics. And I picked A, B, and C because 98 years ago when I was in my 11th grade algebra class, they told me A, B, and C is what you call the coefficients for a quadratic. But I could, if I wanted to, just call these coefficients C2, C1, and C0, just to indicate that C2 is that constant coefficient that multiplies x squared, and C1 is the constant coefficient that multiplies x to the 1 power, and C0 is the constant coefficient that multiplies x to the 0 power. Because x to the 0 is just 1, so that's my constant term. We also said every quadratic polynomial may also be represented in this factored form. And the difference is that for a quadratic polynomial, you get 2 roots. And we said sometimes those roots are even the same number, just repeated twice. And most of the time, they're just 2 different numbers. And we'll look like that. So this is where the new material starts today. We could have a cubic polynomial. And a cubic polynomial is any expression that could be equivalently rearranged and represented like this. We've got c3 x to the 3 power plus c2 x to the 2 power plus c1 x plus c0. And again, I'm naming my coefficients with a little subscript. And the subscript tells you what you're multiplying, right? X to the power what? This is called expanded form. I call C3 my leading coefficient, just like you would expect. Whenever I put a cubic polynomial in factored form, every cubic polynomial still has a factored form, and it looks like this. Instead of 1 or 2 roots, I get 3 different roots. And it could be the case, most of the time, that these numbers are 3 distinct numbers. But you could also imagine a situation where all 3 of the roots are really the same number. Or maybe one of the roots is duplicated, but there's a 3rd distinct root. You know. Those are kind of the three possibilities. And this is what we would call cubic. A quartic polynomial is any expression that could be equivalently represented in this form, where I've got some constant number times x to the fourth, plus some constant number times x to the third, plus some constant times x squared, plus some constant times x, plus a constant term. And every quartic polynomial may also be represented in factored form. In factored form looks like your leading coefficient times x minus your first root times x minus your second root times x minus your third root times x minus your fourth root. And maybe those roots are four distinct numbers. Maybe there's just two numbers that are both duplicated, or there's a whole bunch of different combinations you get with repeated roots for a quartic. And so maybe you're noticing the pattern. I might have a quintic polynomial, and a quintic polynomial would just be some constant that I call C5 times x to the fifth power plus blah, 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 blah. That's how you typed out. And I could also factor every quintic polynomial, but this time I have a leading coefficient times 5 different factors with 5 potentially distinct roots, or maybe they're repeated. This is the last kind of polynomial that gets a name, because we could continue to add more and more factors, and we don't want to have to name all of them, so we stop naming. And what we do, instead of naming them things like linear, quadratic, cubic, quartic, quintic, we just say a polynomial is any expression that can be represented in this expanded form. So in general, a polynomial looks like a constant term plus c1 times x plus c2 x squared plus c3 x cubed plus dot 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 plus cn x to the power n. N can be any number you want, right? I could say n is 27, and then the last term has x to the 27th power. And the dot 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 means use your imagination to fill in everything else, right? If I have x to the 27th power, then that means there could be 27 other terms leading up to that. Little lowercase n is what we call the degree of the polynomial. I say this polynomial has degree n. And maybe you can see now why I'm not labeling the coefficients with like the alphabet. I'm not doing A, B, C, D, E. I'm using little numbers because if I have a polynomial of degree 27, I would have run out of numbers or letters. There's not enough letters for as many polynomials as you want. Okay, so every polynomial of any degree could also be represented in factored form. And the way this looks in factored form is you've got your leading coefficient times x minus your first root to the power m1 times x minus your second root to the power m2 dot 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 x minus your last root raised to the power mk. So once again, factored form looks like you're multiplying a bunch of different factors, where every factor looks like parentheses x minus one of your roots. And the dot 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 here means use your imagination to fill in however many factors you want, right? You can have as many roots as you want, you can have as many factors as you want. k, right here with the little subscript k, that is what we would say is the number of distinct roots. But if the roots are repeated, then they have a kind of multiplicity. And so these little m's that show up in the powers are called multiplicities. If I ask you the degree of a polynomial, and I give you the polynomial in expanded form, you could tell me what the degree is just by looking at the largest power of x. But if I give you a polynomial in factored form, and I ask you what is the degree, what you could do is you could add together all of these multiplicities. And when you add them all up, this adds to be the degree. And that's how you know in factored form what the degree of your polynomial is. So the number of distinct roots is not the same thing as the degree. If all of your roots are distinct, then it would be the same thing. But your roots don't have to be distinct. You could have 4 distinct roots and a degree of 10 if you want to, right? So we'll see some examples like, here I want to find the degree, the leading coefficient, and the constant term for each of these polynomials. In the top left, what's the degree? 4. What's the leading coefficient? 6. And what is the constant term? Negative 5. Okay. Over here in the top right, what's the degree? It's 5. It's the largest power of x, right? Look at the largest power of x. What's the leading coefficient here?
Oh, okay.
It's positive 1. And then what's the constant term? 2. All right. In the second row on the left side, what's the degree here? 3. What's the leading coefficient? Negative 1. And what's the constant term? 0. On this right side over here, what is the degree? 2. What's the leading coefficient? 8. And then what's the constant term? 3. Okay, down here on the left, what's the degree? It's going to be 8. And the reason is because if you see it in expanded form, the degree of a polynomial is just the largest power of x with a non-zero coefficient. And the reason we say non-zero coefficient is if this coefficient's 0, I mean 0 times anything is just 0. So we don't actually, need that. It's just junk, right? It doesn't really do anything at all to contribute to my polynomial. And so what's left is degree 8. What's my leading coefficient here? Negative 1. And then what is my constant? On the right, what's my degree? This is degree 1, because the largest power of x is just x to the 1 power. What's my leading coefficient? 1. And what's my constant term? 2. Okay, on the bottom left here, what's my degree?
4.
This is a little bit of a trick question. If I have x times x times x times x times x times x, that is x raised to the power 6. But multiplication is associative, and that means I can throw in parentheses wherever I want, and it doesn't really change what we're doing. So then if I have x cubed times x cubed, that's still x to the 6th. And that, sorry, that's supposed to be a 6, is just x to the 3 power times itself. So that's like x to the 3 power squared. And so now down here, if I'm going to take the square root of x to the 6th power, that's like taking the square root of x to the 3rd power squared. But if you take the square root of something squared, then the 2 power and the square root cancel each other out. And so this is exactly the same as just x raised to the 3 power. So the degree of this is 3. And the leading coefficient is 1. And the constant term is 0. And there's one last little guy over here. This is a polynomial. And it has a degree of 0. Yeah, so if you just have an old number like this, the number 7, this is a polynomial. It's just a really boring polynomial with degree 0. And the leading coefficient is 7, and the constant term is 7. Yeah. Okay, so now the game is, when a polynomial is given in factored form, the degree is just the sum of the multiplicities of the roots. So this time we're going to find the leading coefficient, we're going to find the roots, their multiplicities, and the degree. So up here in the top left, what's the leading coefficient? 5. What are the roots? (1, -2, +7). What are the multiplicities of these roots? What did you say? No. Each root is going to have a number called the multiplicity associated with it. So like, what's the multiplicity of this root at +1? 2. And you know it's 2 because of this little 2. That's the power of the associated factor, right? So my root positive 1 came from this factor, x minus 1. And that is raised to the power 2. So I say the multiplicity of this root is 2. What are the multiplicity of negative 2 as a root? 3. And what's the multiplicity of 7? 4. Okay, so we found my leading coefficient, we identified what my roots are, and then we found the multiplicity for each root. Then lastly, the degree of this polynomial is 9. And you get the degree by adding together the multiplicities. 2 plus 3 plus 4 is 9. So the degree of this polynomial is 9. All right, moving over here to the right side. The leading coefficient here is 1. Yeah, if there's nothing written out front, that just means the leading coefficient is 1. What are the roots of this polynomial?
-1, +5, -2.
Perfect. -1, +5, and -2. What are the multiplicities of these roots?
1, 2, and 1.
Very good. 1, 2, and 1. Then what's the degree of this polynomial?
4.
4. Because 1 plus 2 plus 1 is 4. All right, in the bottom left, what's the leading coefficient? -1. What are the roots?
+9, -2.
+9, -2, and there's one more root. You say 0? Yeah. 0 is a root because the factor should look like x minus the root, which would be x minus 0. But if I'm doing x minus 0, I'm not obligated to write minus 0. I could just write x. And in this case, if you see x squared right here, that means this little factor, x squared, is associated with this root at 0. So then what is the multiplicity of these 3 roots? Very good. And then the degree of this polynomial is 2033. Just add up the multiplicities. Okay, over here on the right side, the leading coefficient is 1. The roots occur where? Going from left to right, the first one is 0. And then you're right, the next one is -4i. It's okay if the root is imaginary. And then the last part is kind of a trick question. Because the last part isn't fully factored yet. This x squared minus 4, not in completely fully factored form yet. If I want to factor this completely, x squared minus 4 factors as x minus 2 times x plus 2. And so my last two roots are 2 and -2. Okay? What are the multiplicities? We got 4 roots, so I need 4 numbers for their multiplicities from left to right.
7.
1, 3, 1, 1. Very good. And then the degree of this polynomial is 6. Are there any questions about what we just did? Okay.
So wait, what would I actually do? I'm sorry. What would you do if you had an incomplete factor, but you still had a multiplicity on top of the incomplete factor?
Okay. I see what you're saying. That's a good question. So the question is, I think, what would you do if you saw this? If you saw x squared minus 4 raised to the power 3?
Yeah.
So then this little part would become x minus 2, x plus 2, but they would inherit the little 3
Okay.
from first part.
Gotcha. Okay.
Good question. So let's see, which of the following are polynomials? Is this a polynomial? The top left one?
Yeah.
Yes. It's a polynomial, it's an expanded form you get. Is this one a polynomial? Yes. This is a polynomial in factored form. Is this one a polynomial?
Yes. Wait. I was gonna say yes.
This one is a no. And the reason this is not a polynomial is because a polynomial can only get natural number powers of x, right? In expanded form, you only see x to the 0 power, x to the power 1, 2, 3, 4, 5, 6, 7, 8, 9, and on. But you don't get negative powers. Okay. What about this one? Is this a polynomial? Yes. What about this one over here? No, why not?
The power isn't a natural.
Yeah, this is not a natural number. I can't get fractions of powers. What about this one over here? No. I can't get this big square root in the way. It's going to mess everything up. What about this one? I see people saying yes. Why would you say yes if I just told you you can't have a square root? You probably know the answer, just say it. Yeah, the fancy word for it is we say this is a perfect square. So you're right, it factors. How does this factor?
The x is square root, so you get rid of the square. 6.
This radicand where it says x squared minus 6x plus 9,
Oh, that's a factor.
that's a perfect square. And it factors like what kind of factored form?
X plus 3, x minus 3.
It's just x minus 3 squared. And since this is the square root of something squared, that cancels out and it's just x minus 3. And that is a linear polynomial. That's a special case, right? You can allow this little square root thing if you really can take the square root of the radicand and get a polynomial. But that only works if the radicand is a perfect square. And that's actually a very special case. Like x squared plus 1 is not a perfect square. Most polynomials are not perfect squares. So that's pretty rare for it to happen, but in this case, yeah. Man, next Monday and Wednesday, for the rest of the semester, I want you guys to go eat your lunch and then drink like a 32-ounce, 40-ounce coffee before y'all get to class. I see too many people like just trying to quietly sneak in a nap here. I want more answers. And this one right here, do you think that's a polynomial? Yes or no?
No.
No? It definitely doesn't look like a polynomial.
It wouldn't it also be like positive 1 like divided by x minus 1?
What about this? What if I tried to factor the numerator? How would that factor? Be x minus 1 times x minus 1. And then you say, hey, I've got a common factor between my numerator and denominator, so those cancel out. And this is a linear polynomial. It didn't look like that at first, but once you factor, you cancel the common factors. You're like, oh yeah, that is a linear polynomial. Okay. What about this one over here on the left side? I've got x squared minus 2x plus 1 over x minus 2.
It's not.
This one has the same numerator, so I get the same factored form in the numerator. But the issue is, now there's no factors in common with the denominator, so there's nothing that can cancel. And we say this one is not a polynomial, right? It's nothing cancels. And instead, this one has a special name. This one is called a rational function. A rational function is just a ratio of two polynomials. You've got one polynomial in the numerator divided by another polynomial in the denominator, but it doesn't simplify to a polynomial, and that's what we're asking here in this question, so we say no. Okay, what about this one over here on the right side? Is that a polynomial? Why not? So this one is a polynomial, because I still just have x raised to natural number powers. Where you see the square root of 3, that's just a coefficient, you know? Like, yeah, square root of 3 is irrational, but who cares? It's just a number that's multiplying x, and that could be any number. It's really only the powers of x that have to be natural numbers. The 1/2 is just a coefficient, the square root of 3 is just a coefficient, so that's fine. What about this one over here on the left side? This one is not a polynomial. And the reason is because this term 3 to the x, you cannot have 3 raised to the power x. The only thing you're allowed to have for polynomials is x raised to a natural number power. And this doesn't fit the description, and so this is not a polynomial. What about this guy over here? Yes or no? No. Again, same reason. X to the power x is a perfectly fine function on its own, but it's not a polynomial function. And so this is not a polynomial. Negative 42, is that a polynomial? Yes. That's just a boring polynomial of degree 0. And is that a polynomial? No. Any questions before we move on? All right, so we might ask, evaluate the polynomial function at a given point. And, you know, I wonder why I even put this in my notes, because it works just the same as it always has. You're going to look at the point where we're trying to evaluate. This time, the input value is x equals 4. So I go to my function, I rewrite it, but every time I see an x, I'm going to replace it with a 4. And so that's just 64 minus 48 plus 17, which is 16 plus 17, so it's 33. You just replace the x with your input value, and you simplify. Then you get an output value. And that's how functions are supposed to work.
So you can't, real quick, you can't have like irrational values inside the polynomial, right? Somewhere like pi or e.
You can for coefficients. You just can't for the powers of x.
Okay.
Does that make sense? So hold on, I'll show you. It's a good question. This is a perfectly valid polynomial. Even though square root of 2 is irrational, it's just a coefficient here, so I don't care. And even though pi is irrational, it doesn't matter, it's just a coefficient, right? That's fine. This is a polynomial. But what doesn't work is you can't have an irrational power of x, right?
Yeah.
That would be no.
That looks like it could get messy.
Okay. And by the way, those are fine functions. Like in math, you can make a function where it's x to the power of square root of 2. That's okay. The issue is it's just not a polynomial function. A polynomial is a special, very, very simple class of functions that we introduce first in algebra before we do harder stuff. So, now we want to evaluate the polynomial function given right here at the points x equals 0. And at x equals 0, we've got the case where I just rewrite my function, but I'm replacing all of the x's in my function with the number 0, because that's how we evaluate functions. And I get y equals negative 15. What about the other one? if I say I want to evaluate this at x equals -3, it becomes 1/2 times -3 plus 2 times -3 plus 3 times -3 minus 5. And -3 plus 2 is -1, -3 plus 3 is 0, and -3 minus 5 is -8. And so y is equal to 0. Because 0 times anything else is just 0. This will happen anytime you plug in one of the roots of your polynomial. You'll notice in my original polynomial, -3 is one of the roots. And this happens because you get some factor that looks like -3 plus 3, right? And then that's 0, and anything times 0 is 0. So we say the zeros of a polynomial function are the same as the roots of the polynomial because of stuff like this happening. Okay, if I ask you to add or subtract a polynomial, adding is remarkably easy. Like in this example, I've got this polynomial plus this polynomial. But all I'm trying to do is add, and addition has the associative property. And the associative property means I can choose to include parentheses or just forget about parentheses however I want to, as long as I'm just adding. And so in this case, I could just forget about the parentheses altogether. And then to simplify, I'm just going to collect like terms. And I'll also put things in order so that I get 6x to the 4th power minus 3x. There's no terms that have an x squared in it, but I do have two terms with an x, so 3x plus 4x is 7x. And then for my constant terms, I've got -5 plus 1, so it gives me -4. And that's how you add. Subtracting works just about the same way. Subtracting does not have the associative property. So I can't just forget about my parentheses. The important thing to remember when you're subtracting is to distribute the minus sign. And what I mean by that is I get to this point where I want to get rid of the parentheses, but I actually have to say minus x to the 4th power. And then since I'm distributing the minus sign, I'm actually going to say plus x to the 3rd power minus x squared, minus 5x squared, minus 4x minus 8. That's what I mean by distribute the minus sign. And now I just have to collect like terms, and so the largest power that I see around here is minus x to the 4th power. The next largest is x cubed. So I get square root of 2 plus 1 x cubed. The next would be x squared, so I have minus 5x squared. Then I have my x terms. And I've got two terms that have an x in them. And so I need to add -5/2 and -4. So I have to find a common denominator. And that's going to be -5/2 minus 8/2. So it would be -13/2. And then lastly, I have my constants. My constants are 3 minus 8, so that's minus 5. So if you're subtracting, just remember to distribute the minus sign. Any questions about adding and subtracting? Hopefully that works how you think it would work. Hopefully it's intuitive. The next thing we're going to do is multiply. So this time I want to multiply these polynomials. This is how I'm going to do this. I'm going to try to find the area of this rectangle. And this side length across the top of my rectangle is going to have side length 6x to the 4th power plus 3x minus 5. And I can partition that into 3 little segments. And then the other side of my rectangle is going to have the length negative x cubed plus 4x plus 1. And multiplying these polynomials is going to be equivalent to finding the area of this big rectangle. And the easiest way to do that is to segment this large rectangle into 9 smaller rectangles. And we find the area and we add them up. So here, we've got 6x to the 4th power times negative x to the 3 power. And that's going to be negative 6 times x to the power 7. Very good. Okay, 3x times negative x cubed is negative 3x to the 4th. Negative 5 times negative x cubed is going to be plus 5x cubed. 6x to the 4th times 4x is going to be 24 x to the 5th power. And then 3x times 4x is plus 12x squared. And negative 5 times 4x is minus 20x. And all of these things times positive 1 is just going to end up giving me 6x to the 4th, 3x, and negative 5. So now when I add things up, I say I'm going to get negative 6x to the 7th first. There's nothing I see that has x to the 6th power in there, but there is a term that has x to the 5th power. And then I actually have 2 different terms that contain x to the 4th power. So I've got to add both of those together and end up with positive 3x to the 4th power. The next thing is x to the 3rd power, which is plus 5x to the 3 power. And the next thing is x to the 2 power and x to the 1 power. Take care that there's 2 different terms that contain x to the 1 power. And that's my answer. Is that super easy? Okay. So we can add, we can subtract, we can multiply. We're going to save division for next time. We'll save that for next Monday. The next thing we might want to do is expand. So this polynomial is given to us here in factored form. And the process of rewriting this in expanded form is going to involve taking 2 of the factors. Like I just arbitrarily chose x plus 3 times x minus 5. And we multiply. And we multiply the same way I always multiply. And in the end, I can write this as 1/2 times x plus 2 times x squared minus 2x minus 15. That was my first step. And the next step is I take these factors and I multiply those. So I multiply x plus 2 times x squared minus 2x minus 15. And this is what I get. One half times x cubed minus 19x minus 30. And then the last step here, we're almost at our answer. I just have to distribute that 1/2. And I get 1/2, sorry, that's a 2, x cubed minus 19 halves x minus 15. And that, you'll notice, that's an expanded form. So this is a big skill. You just learned how to take a polynomial written in factored form and expand it so that it's written in expanded form. This one was a cubic polynomial, right? It had 3 different factors. We've already done this with the quadratic polynomial, and you can probably imagine how to do it with a quartic polynomial or higher degrees. It would just take a lot longer because there's a lot more steps of multiplying, right? Basically, whatever the degree of the polynomial is, that's how many steps you're left to take, right? And since this was degree 3, we had to multiply once, twice, and then distribute. So degree 4 would require you to multiply 3 times and then distribute. So here's one. Write a polynomial function in factored form that meets the given description. And the description says, I've got roots at x equals -4, -1, and +3. And those roots have the multiplicities 2, 1, and 1, respectively. So let's see what this looks like. I'm talking about factored form. And factored form looks like this. If I have a polynomial with 3 distinct roots, then that's what it is. That's the factored form. Now I don't know what my leading coefficient is, so I'll just write a for right now. Maybe we can go back and fix that later. But then my first factor should look like what? X plus 4. Raised to the power 2. And then my second factor should look like
X plus 1.
X plus 1. And the last factor looks like
X minus 3.
X minus 3. Okay, this is almost the correct answer. I just don't know what my leading coefficient is. But we can find my leading coefficient if we use the second clue here. It says the y-intercept is y equals 6. But at the y-intercept, x is equal to 0. Yeah, the y-intercept means x is equal to 0. And in this case, y is equal to 6. So using this information, I'm going to rewrite my function, but I'm going to replace y with 6, and I'm going to replace x with 0. And then I get 6 equals a times 4 squared, which is 16. 16 times 1 is 16. And 16 times negative 3 is negative 48. Very good. And so we're almost there in terms of solving for a. I would just want to divide both sides by negative 48 and then simplify that fraction. Yeah. So a is negative 1 over 8. So right here, I'm actually ready to answer my question. I don't need to write an a here anymore, so I could erase that. And I could go back and I could put in my negative 1 over 8. Right there where it belongs as my leading coefficient. And then I can circle it or put a box around it, because that's my answer. Does that make sense? So another question that's super, super similar, I'll point out the difference, says, write a polynomial function in expanded form that meets the given description. And it says the roots are at x equals negative 3, negative 2, positive 4 with multiplicities 1, 2, and 1. The y-intercept is at negative 8. This is all exactly the same, except I'm trying to write this in expanded form. So step number 1, we are not going to try to go directly into the expanded form. That would be just about impossible. But step number 1 is to first write this in factored form. Just like I showed you in the previous example. And so if you go back and rewatch the previous example, you know exactly how to do that. And then step number 2, we're going to take whatever we got from step number 1 and expand that. And you've already done this skill too, right? You have already taken a previous polynomial in factored form and rewritten it in expanded form. And you know how to take a description like this and write it in the factored form. Now, for this kind of question, you just have to link those two skills together. You write it in factored form first, and then you expand. So I'm going to save you guys a little bit of time. And we'll just leave that like this. Now that you know how to do it. I said this, with quadratic polynomials, but this makes sense for polynomials in general. If I say the word polynomial, I'm only talking about the expression. This is an example of just an expression. And polynomials have certain roots. If I were to factor this polynomial, I could see what the roots are based on the factored form of that expression. Alternatively, if I use the word function, the word function means that I have y equals some function of x, right? Y equals some polynomial in this case. And functions have zeros, but the zero of a polynomial function is the same thing as the roots of the polynomial. I mentioned that earlier. Now if I say the word polynomial equation, a polynomial equation is just any equation that you can write. And you can use your algebra skills to rearrange it so that the left side of the equation is a polynomial and the right side of the equation is 0. If that's possible to rewrite it this way, then we call it a polynomial equation. And equations have solutions. And you'll notice the solution to this equation those are just the roots of the polynomial. And so that's why it's going to be useful for us to learn how to factor polynomials. That way we can solve more types of equations. The next thing that it says down here is the degree of a polynomial equation is also the least upper bound on the number of possible solutions. Normally, if I see a polynomial equation that looks like this, I don't know what the solutions are just by looking at it, right? This is an expanded form, so I can't tell what the roots are right away. And so if I don't know what the roots are, I don't know what the solutions are, and I don't know how many solutions there are. But what I can do is I can tell from the degree that this equation has up to 3 solutions. In other words, it does not have 4 solutions. It does not have 5 solutions. It does not have 6 solutions. The only possibility here is that there is 3 solutions corresponding to the 3 roots of this polynomial. Or maybe there's just 2 solutions because one of the roots is repeated. Or maybe there's only 1 solution because there's 1 root repeated 3 times, right? But there's either 1, 2, or 3 solutions. So you can tell from the degree how many solutions there might be. And let's take a look at these examples. So looking at this equation, how many solutions are there? I think I heard somebody say 6. So the number of solutions is either 1, 2, 3, 4, 5, or 6. What about this one? There could be 1 or 2 or 3 or 4 solutions, but not 5. What about this equation? There could be up to 5 different solutions. Same for that one. What about this guy? Seven? Yeah, you can actually lower that ceiling to just 4 if you realize you could just subtract x to the 7th power from both sides, and then it simplifies to a degree 4 polynomial equation. Let me show you some examples using wolframalpha.com. So wolframalpha.com. Here's one, x to the 5th power plus 10x to the 4th power plus 40x to the 3rd power plus 80x squared plus 80x plus 32 equals 0. If you were looking at that equation, how many solutions could that equation have? It could have up to 5, right? It definitely can't have 6, but since the degree is 5, it could have up to 5 solutions. And Wolfram Alpha is neat because it'll just find the solutions for you. And Wolfram Alpha tells me there is just one solution. And the solution is x equals -2, because if I were able to factor this, this would be the factored form. It would be x plus 2, so just one root at x equals -2. And that root has a multiplicity of 5. So the whole degree of this polynomial is wrapped up in that one root's multiplicity. On the other hand, if I had something like x raised to the 5th power equals 1, how many solutions could that equation possibly have? It could have up to 5, because the degree of the equation is 5. Can you think of any solutions? Yeah, the number 1, because 1 raised to the 5th power is just 1. Does negative 1 work?
No.
No. No, because negative 1 to the 5th power is negative 1. And if it was a number larger than 1, it doesn't work, because to the 5th power, that would make it bigger. And if it's smaller than 1, raising it to the 5th power doesn't work, because that would make it smaller, right?
I mean, it could
So
technically.
the only real solution here is the number 1. Okay?
Could also be not like that.
Yeah, that's the same number, though. It's the same number. So there's only one real number solution. It's x equals 1. And the other 4 solutions here are complex numbers. So when I say it could have up to 5 solutions, you know, it doesn't always have 5 solutions. Maybe it just has 1 solution. But also, you could have 5 solutions where all 5 of them are complex numbers, or like in this case, 1 of them is real, and the other 4 happen to be complex numbers with a real part plus or minus an imaginary part. But anyways. Our goal in the next 3 weeks is going to be this. We're going to want to recognize polynomials when we see them in expanded form and be able to tell what's their leading coefficient, what's their degree, what's their constant term, what are, you know, what's their deal. We want to recognize polynomials in factored form. We want to know what are their roots, what are the multiplicities, what's the leading coefficient, what's their degree. Today, we already learned how to expand a polynomial given in factored form. And next time we meet, basically all of next week, we're going to work on factoring polynomials. That's the harder part. Factoring is always harder to go from expanded form to factored form. And then section 3.4 is going to be about taking a factored form polynomial and graphing it. So we'll do that in the next few weeks. And like I mentioned at the start of class, the rest of chapter 3 is just rational functions. And once you are a complete wizard at polynomials, then rational functions will be super easy. So that's the plan.